Hey, thank you guys for coming to the talk, and thank you for organizing this and inviting me over here. So quick introduction. My name is Ajeet. I am a manager on the recommendations team at Twitter. We are a group of engineers and data scientists who are powering like a few different parts of the product. If you guys have worked, or if you guys use Twitter, there's who to follow modules, and there's various different components on Twitter that are powered by this team. Today, I'm gonna give you like a bit of an inside look into some of the components that we have that power many of these systems. So at a high level, we'll do an overview of the different recommendation systems that we have in the first part. The second part is going to talk about account recommendations. And in the last part, I'll talk about the challenges associated with serving some of these recommendations in real time. All right, so recommendations. Why do we need recommendations? At Twitter, we want to enable our users to stay informed about the world, and recommendations plays a key role in here because there's just way too much information on the platform, and the system and Twitter needs to do a lot of the heavy lifting to surface the content that the user is interested in, so that they are finding relevant conversations or relevant people that they would be interested in hearing about. And that's the job of recommendations. We try to build some of these infrastructures that power these systems. So what are the different surface areas that we work on? This is the notifications tab. So since Twitter is inherently real-time, notifications are a key part of keeping users informed about something that's happening on the platform. And this screen shows the notifications tab, where you see a few recommendations that have been pushed to users. Another area that we work on is emails. Email recommendations, which you see one of the type of emails here, which is called highlights. These are targeted to maybe a different set of users, and they have slightly different goals. We'll get into that in a little bit. We talked about people recommendations, and people recommendations, so on Twitter, you follow an account and you get content into your home timeline, and therefore we want users to follow high quality accounts that we think that they're interested in, and therefore we want to build like a good user recommendation or account recommendation system. And finally, this is our Explore tab, which serves a slightly different purpose, where we are surfacing content or conversations that may be of interest to a broad set of users, even if we have, and especially if we have low amount of signal for those users. So for new users or for people who are coming back to the platform and who haven't put in a lot of time on figuring out what are the accounts they want to follow, this page is extremely useful. All right, so at a high level, we have different recommendation types. We have accounts, we have tweets, we have topics. And then we power these different products. WTF is, can anyone guess what WTF is? Who to follow. Who to follow is one of the is what we call our account recommendation system. Explore is the screen that you guys just saw, which was showcasing like the trends and topics of conversation on the platform. And users consume our recommendations by going to these products. The other channel that we have is when users are off platform, and these are what we call the reactivation channels, where we can send a user a push notification or an email and get them to come back onto the platform if we think that the content that we deliver is of significant value to the users. All right, cool. So let's talk about like the overall anatomy of a recommender. At a high level, what we want to do, and this is the reason we're talking about this is because there are many different, as you know, recommendation systems as you've seen in the past. So there are some common patterns across all of these recommenders that we use consistently. At a high level, we need to generate candidates in some form, and there may be different algorithms for generating these candidates. We might generate candidates that are popular in a geolocation, or we might generate candidates that are popular in your network. That's the first step. The second step is to rank and filter these before showing them to a user. And often when you're starting off building a recommender system, you want to rely on business rules to bootstrap your recommender system. And for example, some business rules that we have are, we want to send only one email a day, or we want to send this email at a particular time. These rules come in handy because they are kind of, our product intuitions are kind of embedded in these rules, and we can start to implement a recommender system based on these intuitions. So essentially you start without any machine learning, and the idea is to get to an experiment quickly. All right, which leads us to experimentation. How many folks here, just as a quick survey, know what experimentation is or have done an experiment in the past? All right, so about 50%, I would say. Okay, so experimentation is like an industry standard. We do what we call A/B tests, where the goal of an experiment is to determine a causal relationship between product changes and metrics. What do I mean by causal relationship? So we want to make sure that some metric on the platform has increased because of a product change. And this may not always be obvious if you just look at time series data. And that's where experimentation comes in. What are the metrics that we want to track? So there are business metrics that any business would care about. We care about DAU, engagements on platform, the amount of money we are making. We also care about some leading indicators for our products. And we'll get into more of that in a second. And finally, we care about negative metrics like, are we spamming, are we generating more spam, or are we causing more users to opt out of push notifications, for example. So let's talk about leading indicators. What are leading indicators and why are they important? Leading indicators are the first indicator in your experiment, which is going to be somewhat easy to move. Some of the business metrics that we have are often a little bit further removed from the product and are harder to move. A good example is maybe DAU, right? Changing some ranking in some sub-product may not directly be moving a big business metric like DAU, but you still need to make those product decisions. So you rely on like the top level leading indicators there. For example, with trends, a good business metric might be driving up conversation on the platform, and this is probably harder to move on every single experiment. But a leading indicator maybe clicks on trends. A better leading indicator would be engagement on the landing page of trends, which is better because we are not optimizing for clickbaity things. And sure, so we have these leading indicators, but how do we know whether these leading indicators are impacting the metrics that the business cares about? And one of the patterns that we use at Twitter across different recommendation systems is we keep longer term holdback experiments. So we might do something like, over a quarter or over an even longer period, have some set of users on a different experience than others to measure like the impact over a larger period of time. All right, so coming back to the anatomy of a recommender. So we generate candidates, we want to do some ranking. What often happens is that rules and heuristics get cumbersome to maintain. For example, we might have some rules that we want to show. We have multiple different algorithm types, and now we want to kind of figure out which algorithm is performing better. And we might hand code a rule saying that show candidates from this algorithm more than another, and weight some algorithm more than some other algorithm. This might work, and it's a good way to get your changes out. Unfortunately, rules are suboptimal with respect to metrics. It is much better to frame it as an optimization problem to be solved using ML. For example, you can directly optimize maybe for the leading indicator, saying that we'll just optimize for clicks. And that's where what you want to do is you want to extract features from candidates, you want to extract user actions, you want to join those things, and you want to construct a model that can be used in ranking. And how do you determine what do you want to improve? Do you want to improve your model? Do you want to improve your candidate generation? Do you want to improve what do you improve when you work on these products? Improvements to any component can improve the overall metrics and the overall recommendation system. And also the one complication is that changes to one component can impact others. For example, adding more candidates with a different set of features will require you to retrain and maybe change your model latency, change the behavior of the recommender system in general. So what should we improve? Well, it varies by product. You want to build intuition from your prior experiments that you have run and come up with newer experiments that you want to test out. In general, a rule of thumb is that changes to your product give you much better wins in general than better candidate generation, and that is a little bit better. Gives you it's good to focus on that as compared to modeling. And these are just general rules of thumb, and maybe these are very specific to Twitter and our experience, and we'll get into why in a little bit. So what are the challenges for Twitter? So on candidate generation, in general at Twitter, there's billions of potential candidates. So the reason this is the case is because Twitter is a public platform. So every piece of content that is generated on the platform is a candidate recommendation to every user. And what that means is you can pretty much think of it as a giant matrix where you have like the set of users on one axis and the set of all the candidates being generated on another axis, and you want to put in a score you want to fill this matrix up. Obviously, that's infeasible. So you can't really rank everything. So this is why you need to generate high quality candidates to start with. Another important challenge is feature generation. So in our experiments, most of our impactful features are edge-based, which is rather than, so when you're recommending a candidate to a user, you can generate many types of features. You can generate candidate-only features, that hey, this candidate is about this topic. Or you can generate user-only features, hey, this user is in this cohort, or this user is, it has logged in X number of days ago, or whatever it is. And then you can generate these edge features, which are the user-candidate pair features, or user-author pair features. We've observed that those features are very expensive to compute and store, but are also the most impactful. All right, so let's talk about account recommendations. So in our beautiful flowchart of all of recommendations, that's the yellow box there. It's the account recommendation type. What's the job for account recommendations? Well, it's mainly to connect users on Twitter. And the reason we need, again, recommendations here is because any user is a potential candidate recommendation to every user. So Twitter wants to do the heavy lifting. This is maybe different from some of the other cases where you only care mainly about like one way to do this would be to only care about like your address book or phone book or those kinds of users. But in general, the problem for Twitter is account recommendation problem for Twitter is slightly larger. So for account recommendations, there are many different product surfaces. Here is one. This is the Connect tab where you're showing a user a bunch of accounts that we think they want to follow. You can see some context up top because they follow these accounts, and we think that these additional accounts are good candidates to follow. What are the business metrics for for Twitter. For this platform, again, the business metrics don't change that much by sub product. They would again be DAU, engagement, time spent on the platform. And what are your leading indicators? Your leading indicators are mainly follows and mutual follows. Excuse me. So as we were talking about, there's a massive candidate space, and most candidates are uninteresting. So generating high quality candidates is important. Follow graph doesn't change as frequently. So excuse me. The follow graph doesn't change as frequently. So one of the algorithms that we use is we try to figure out what accounts users follow, and based on that suggest additional accounts that they might want to follow. The follow graph itself doesn't change so frequently, so we can do a lot of processing offline. How do we find interesting candidates? Address book is one signal. There are others as we'll get into. Excuse me. For account recommendations, your 2-hop follow neighborhood is an important source of candidates that we want to recommend to a user. In this case, in the graph, and it's good to kind of clear this terminology up front. A is the user who we are recommending content to. A follows the users B1 and B2, who in turn follow C. And C is the candidate recommendation. We call B1 and B2 your social context. So basically, we are seeing who are the people that the people I follow. There are lots of other techniques, but in this case, you can see that Anton is a candidate recommendation for me, and Anton would be the C in this case in terms of the notation, and Anton is followed by some social context, Naz, Chan, and Tian. There are lots of other techniques that we can use to generate these recommendations, for example, similar accounts, determining strong ties between users, and so on. Let's talk about mutual follows. So suppose as a product, we want to test the hypothesis that mutual follows drive engagement on the platform. Again, our notation is A is a target user, C is a candidate recommendation. How do we generate mutual follow candidates? So what we can do is we can find all users who follow the target user. So find all C's who already follow the A, and then recommend C to A as a candidate. Unfortunately, not all such accounts are interesting. For example, if I'm the user who's visiting Twitter and you show me everyone who follows me, I might see recommendations which are just people trying to game the follower count by just follow spamming users. So there might be some random account just following a bunch of other accounts, and now all of a sudden that's a candidate recommendation for you. So we need to find better candidates, and this goes back to why candidate generation is an important step. So how do we do that? Well, what we can do is we can see if there is a social context for that C. So if someone follows me, I follow someone else who follows that person, that might be a good signal, because that gives me a social context. There is someone else who's done the work of understanding and following that user. So we get to this triangular loop, which is the A follows B, B follows C, C follows A. And that's one algorithm to generate candidates for a given target user. Okay, and here maybe you guys can take a picture, but this is like a take-home puzzle. How do we find all such triangles? The problem is framed in a slightly different way on the right. Basically, for every social context B, there's a bunch of users who follow this account. There's a bunch of C's that B follows. The real question is to figure out which of these m times n edges exist. The framework here is we are working with on offline, so we have like a MapReduce framework where we have a bunch of as input directed edges on Hadoop. Your output is to return all triangles. So why is this non-trivial? Some nodes can have a very large in or out degree. For example, Lady Gaga, I think, is followed by about 100 million users today. So how do you scale your offline job to be able to handle such cases? If you have a reasonable, a good solution that you think works, please DM me. Bonus question is how do you efficiently update these graphs? And yeah, that's a bonus question. So as we talked about, follow graphs change slowly over time. So suppose you've generated candidates yesterday and you have a delta graph today. How do you merge and generate new candidates? Cool. All right, so now you have some system for generating all these candidates based on triangular loops. Maybe you should start experimenting it. Before experimentation, it's good to understand what the coverage is. What is our you want to basically go for high coverage experiments, because those are the ones that if you do a good job of coverage and probability of engagement, then you will have a higher impact on the entire platform. Our leading indicator here obviously is an outbound mutual follow, which is someone is closing the loop of follows, as opposed to, say, opening the loop, which is a separate, different but also interesting problem. Once you are satisfied that this is the right thing, you add the candidate to the list of candidate selection algorithms for your treatment bucket. One caveat is let's talk about like the network effect that this introduces. So on Twitter, our recommendations that we surface here are themselves users on the platform. So an interesting dynamic here is, if you change your algorithm for people, if I change my algorithm to show different candidates in my recommender for me, that might change my behavior, but it might also change and impact the behavior of users who are in that who to follow module. So we call this, the distinction here is there are engager side and receiver side experiments. And this is a common pattern in other parts of the product as well. A good question is, why can't we, or at least a non-trivial question is, why can't we measure this entirely on the engager side? So for example, I want to see what the impact on the receiver is. Why not just look at what the engagers are doing? And the answer for that is that the populations are different. The kinds of people who will show up in the receiver, on the receiver side, are different, and that's why you need to measure that separately. As an example of what I mean by receiver side experiment, in who to follow module, if a receiver experiment says that you know what, we are going to hold back on some receiver or some algorithm, then maybe we will not show this particular candidate to any user on Twitter, and then measure the impact on that user, for example. Yep. So this was an experiment that we actually ran, I think a quarter ago or so, and we saw huge gains in engagement. Cool. And now let's move on to real-time recommendations. This is a slightly different track, in the sense that we're going to be talking about a system that generates, and some of the trade-offs that we see while generating recommendations in real time. All right, so real-time notifications. Twitter is a real-time product, and push notifications are a channel for us to be able to deliver value to users in real time, which means that latency in recommendations matters. An example here for why latency matters is, suppose a user goes live on the platform. We want to notify people who might be interested in that broadcast as soon as possible with low latency. There's a natural trade-off between latency and relevance for push notifications. How we frame it as internally as an optimization problem is, given a budget of, say, 1 push notification or n push notifications per day, how do we maximize the value that to our business and to our users? Examples of such notifications, we already talked about the broadcast example. Another example is again, if you look at the right, we keep coming back to this graph, but we want to notify the user A when n people that they follow, say B1 and B2, engage with the same content C. So this is what we call MagicRecs, which is a product we launched, I think about 4 years ago. Notation again is important, and I apologize in advance for these slides. There's a lot of notation here, so it might be going by a little fast. I'll have time for questions later. So the notation is A is the target user who is getting notified. So if I am viewing Twitter on my platform, I get a push notification, I am A. B is the social context, which is if I follow someone, that person made some interaction and caused a push notification to me. So that the person that I follow is what we call the social context. And C is the candidate recommendation, and these could be tweets, users, and so on. So what are the challenges here? Twitter is a, so how many of you have heard of the fire hose? Cool, yeah, so a lot of you. So Twitter has Twitter has a fire hose that is a service that we provide externally as well, which is like the set of all tweets and engagements that happen on the platform. We have a similar system internally, so we get like an input stream of events, which we in terms of notation is B engaged with C are the notation. So for example, user B tweeted C, or user B followed user C, so on. What we want to do is we want to generate recommendations for A. Why is this challenging to do this in real time? For every B2C event, so every B2C event is potentially interesting to all the followers of B. Sorry, to all the followers of B. There's an error on the slides. So the number of potential events is the size of the fire hose, the number of events we see, multiplied by the fanout factor. And the fanout factor on Twitter is very large. In addition, another challenge is graph skew creates spiky behavior. What do I mean by that? So we talked about how Lady Gaga has like a lot of followers, Katy Perry has a lot of followers. So when these users generate content or engage with some content, the number of people who are target users for those people is very large. So it generates a spike in the amount of potential candidates that we are generating. This is also exacerbated by spikiness in real world events. So in the real world, Twitter usage spikes when there's a real world event, whether there is there's some news event, there's sports, or whatever it is. And these are inherently spiky. There's not a uniform set of events happening over time in the world. So that spikiness is exacerbated. These systems have to deal with that spikiness as well. So how do we generate recommendations how do we generate these recommendations in real time? So one option is a pull-based solution. What do I mean by a pull-based solution? Basically, given a user A, so we just loop over all users. So say we know we know the entire set of users, we know their push tokens. We just loop over all these users, and we look up. We keep track from the input stream. We keep track of what are people engaging with. Then we loop over target users, find out what their social context is doing, generate a candidate recommendation, and push. This works. This is actually we use variants of this in many places. The challenges here are getting to low latency is very hard, because to get to low latency, say you loop over all your users in 1 hour. To get it to 30 minutes, you have to double your QPS to downstream services, and you can't keep doing that. So if you want latency of few seconds, you can't do this really fast loop. You can do variants of this, like maybe for some experiments you might set up a quick loop, but in general, for at scale, this is a bit tricky. And also other challenges are how do you store these graphs. So the recommendation on the bottom is an important one to keep in mind. So this is a push notification that was sent to a user. You see that it follows that pattern of A engaged with B, which A follows B1 and B2, which engage with C. So this user follows Nas, a few other users who liked this photo. That's the kind of notification that we're trying to generate. So how do we do this in real time? Like, how do we generate this? So one option is assume that you have infinite memory on some machine. You can store the follow graph in local memory. Whenever you see a B2C event, you look up all the A's that follow B and generate C as a candidate recommendation. So basically you keep the transpose of the follow graph, and you listen to incoming events, fan it out to that transpose. Unfortunately, or fortunately, the follow graph is massive, so we need to distribute. Right. Let's talk about cross partitioning. So the graph service that I'm describing here is over the next couple of slides is an in-house system that we've built, which is a multi-tenant graph partition graph system, which solves some of these problems. So the follow graph is very large and very skewed. We want to distribute processes across many nodes. So how do you go about partitioning a graph? A simple way to do it is to partition by the target user. So in our overall system, what we want to do is we want some node to be responsible for a subset of target users. And once we have that, what we do is we partition our graph in a way where we keep two types of partitions. So on the right is an example. The input graph is provided there as a simple input graph. The lightly shaded nodes are the target users. Suppose there's only two types of partitions, an even partition and an odd partition. The even one is the row on the top, the odd one is the row at the bottom, and you're considering the graph and its transpose. The transpose is important because of fanout. So we want to look at both the graph and its transpose. We partition by users such that we keep all the edges on both the forward graph and the transpose on the same node. So in this case, what that means is we will key the people who that subset of users follows. We are partitioning by the lighter shades. So all the users, so the even partition will keep all the users that are followed by this user, as well as the transpose, which is all the users that follow this user. Does that make sense? Cool. Okay. Right. And before we dive into what each machine does, maybe let's take the font is kind of small, but let's take a look at how all of this is kept in like how the overall system works. So we have a proxy layer. So this cluster of there's a cluster of machines over which this partitioned follow graph is stored. And we want this to also respond to graph queries and generate some real-time candidates. What is a graph query? An example query is given here. Given a user A and a hashtag H, who are the people that A follows who have engaged with this hashtag? And it's kind of hard to see, but if you look at hashtag 49ers, there is someone that I follow who's tweeting about this. So that's the kind of query. Given an A and a C, in terms of our notation, given an A and a C, give me all the Bs, basically. Each machine here, so there's a proxy layer. So what happens is, since each machine is responsible for a subset of target users, we need a proxying step where when a request comes in, it figures out which machine is responsible for that target user, redirects the query there, runs the graph query locally, returns it back. So that's the service side. Let's look at what is stored on an individual node. So in this chunk, so on the left side, what you see is there's an incoming stream of B2C engagement events, and at the bottom there are recommendation candidates that are piped out. That is our fanout pipeline. That's a real-time recommendation pipeline. On the far right, you see the graph query processor. This is the thing that's going to return, given an A and a C, give me all the social context. The stuff in the middle is the graphs. So the purple the purple rectangles are your real-time graphs that you're keeping in memory. Your the green and the red chunks there are the graphs partitioned, the partition follow graph that you computed earlier. Often what we'll do is we'll compute these graph partitions offline and download them locally onto a machine and start serving these requests. So that's the overall setup. Each machine, the key part here is that each machine is responsible for only a small set of target users. So coming back to the example, for social context queries, given a user hashtag pair A, C, an algorithm that this graph query processor runs is look up all the Bs that A follows, and for each B, check if C is in the engagement. So look at the engagement graph, which are the purple graphs kept in real time, and look at the forward graph for A, which is the green forward graph here for that set of users. This is partitioned, and return all the people that A follows that have engaged with that hashtag. And this is like a social context query. Another example is live notifications. Suppose B went live, and now in this part we are focusing on the left hand side, right? So we're looking at only the fan out pipeline. So in this case, suppose B goes live, B to broadcast ID event shows up in the engagement event stream. We look up the subset of users who follow B and who belong in this shard. This is the red transpose graph partition. And we fan out the broadcast ID to those users, and we write those recommendations to the queue. This is a little bit harder, so I can go over this quickly, but here, so this is the MagicRecs event type fanout, where where if k people like a tweet, we will generate a fanout recommendation. So here, again, what we'll do is we'll look up. Here we have to look up both the forward graph and the reverse graph. Given an incoming B2C event, we look up all the users that follow B. That's the transpose fanout. Then for each of those users, we look up all the people that they follow, which is the forward lookup. And then we find users among that forward lookup who have engaged with C. And if it exceeds the threshold, we write that event out. This part is a bit dense, but you can trust me, it works. And that's all that I have for today. Thank you all for patiently listening. And do you have any questions?
Great, fantastic talk. Thank you, Ajeet. We do have time for questions. Start back here.
Yes, thank you for that. I was wondering if you also looked at people, the blog users, or are muting them, and how that will affect on making these decisions.
Yeah, that's a great question. There are, in addition to all of to these kind of candidates, we just don't send those out directly. There are a lot of business rules in place. So if a user has blocked another user, we will not serve that user as a recommendation, for example. Or if it's muted, we have like checks at the final layer to make sure that we are not sending such recommendations.
Okay, any more questions now?
So I have two questions. First one is like, Finally, suppose you recommend A with some C, but the A already follow them already, right? Or multiple things there. So do you all have some like criteria, like a rule engine to decide which one to recommend A?
Yeah, we do have filters. So just like blocks, there is a, if you've already engaged, if we've already shown you some content, we don't need to keep showing you that content. There is also the larger, like there are also other rules around fatigue. So if you want to show you some recommendation, we've shown that many times in the past, we may not show that again and again to you. So there's a few rules like that.
I thought we had one more question in the back. Great.
Thanks for the awesome talk. Do you guys do pure content-based recommendations? And if not, why not?
Can you maybe clarify what you mean by content-based recommendations?
So let's say I'm not connected by user or degree is high, and I'm interested in 49ers, you're interested in 49ers. Are you going to start recommending me?
Yes. So you're talking about something similar to collaborative filtering, or?
Not necessarily. So let's say there is no context like in user connections whatsoever, but the content is relevant. So I'm posting stuff about 49ers.
Right.
You just look at the tweet contents, no connections between the users or whatsoever.
Right. So we do that. We do that to some extent. We are actively working to improve some of our systems there. But a lot of the work on Explore is targeting based on interests rather than graphs. Yeah.
Okay, and if that's it, well, why don't we thank Ajeet one more time?
Thank you.